Hi, this is Bill Foote, and it's Stats 1. We're in the region of Lecture 5, and this is Part 2, one of two parts of Lecture 5. We are working with Carl Friedrich Gauss. He's unfortunately no longer with us, but his models and his robots certainly are. And what we're going to do in this part is implement what we talked about during the part 1 lecture. And you can see here, this is very much the same way that we will proceed. We proceeded from the binomial and repurposed it into the Poisson. So we're going from lecture 3 to lecture 4. And here's the result of lecture 4's, part 3 there. Where we implemented the Poisson model. Here it is in all its glory. Now we're going to repurpose this model and make it a Gaussian or normal curve model. And we talked in the last lecture about how, over here you can see it in the blue, how it gets kind of pinched in. We're able to see quite a bit here in the tails. It's kind of pinched in. It's kind of an inflection point. There's a very strong concentration around the mean of, in this case, the number of workers. We're going to find a very, very similar situation with the normal curve. In fact, the normal curve will be symmetric by definition. It's looking at deviations from the mean, and large deviations will have very low probability. Large negative and large positive deviations will have very, very low plausibility or probability, just like in the Poisson. And if we could have made a similar picture of the binomial. All of these are highly convergent series. They converge around some central locating attractor of probability, and it's a very strong attractor. Well, you guessed it, there's probably other distributions that diverge. One of them is the exponential, especially a gamma exponential, which is not in the scope of this course, but would be in a second half of this course, part 2 of this whole course. And those are extreme value distributions. Those are distributions of events that most likely would occur in the tails. And of course, we will repurpose this, and there's a bunch of things we need to do. First thing we need to think about is the data doesn't have to be integer anymore. It can be anything. It could be, even in this one, I hazard to put it in here. What if this was 2.45? Yeah, seems to work. What if this was, instead of 8, 8.12? Okay. And it does seem to work. Instead of 4, 3.49. Yep, does seem to work. You can see it moving. So the Poisson can be generalized to include non-integer numbers, and it does so by generalizing what a factorial is. And the factorial, it's why the gamma function was invented, is the interpolation between a factorial of 3 or a factorial of 4. That's the general idea behind it. Well, let's use a function. As a matter of fact, this generalization ends up being the normal curve in the limit, little calculus concept. There are 2 parameters, though. Remember when we posed the question, we were asking, what is the most plausible level of performance given that we have levels of performance and two different regimes of performance, a low volatility and a high volatility performance regime, two different regimes. And what this gives rise to is a mean and a standard deviation. That's how we would parameterize that, the terms of that question. And thus we could form hypotheses that, as we did in the lecture, we would have a range of levels of average performance. And we can take, for example, our grade point average system that we use in education, which is a number between 0 and 4 inclusive. 4 being highest, 0 being, well, we know what 0 is. Yes, we want to avoid that one. We're actually going to go between 1 and 4. Okay? And we can form 5 hypotheses of those, but we need to use those 5 hypothetical levels of performance and do it for each of 2 levels of volatility or uncertainty about performance. Okay? That's how we're going to look at this. And instead of lambda, we would have here mu. So we could change that right away. We could have mu. And instead of a max of 14, we'd have a max of 4 and a minimum of 1. Notice the curves are going to change radically here. But it's only going to be 4 intervals. And that's going to be kind of crazy here. So we have a width of 0.75. And if we do this across all of these hypotheses, you see it doesn't work out very well. So we got to start engineering this as we did. We want to go from 1 to 4 and 1 to 4. First of all, we have 1 too many hypotheses. We only need 10. Well, that was the first thing we discovered in the lecture. So let's get rid of one of these. And we can do so pretty easily just by putting a cursor, let's say 14, somewhere in the range, not at either end. Go up to the delete and delete rows. Now we're blowing things up a bit. Okay, don't worry about it. Okay, the model blows up. Okay, we will fix that. Hypotheses can be fixed pretty easily. Control down. There we go. Now we have 10 hypotheses. And we have the first 4 here. Okay, so 1, 2, 3, 4, 5. 5 hypotheses, and we have from 1 to 4. Now we start a new set of 1 to 4 by going back to the minimum. Center. You can see it just replicates itself. This isn't too bad. Okay. Well, that, who knows what's going on over there? Okay, that's kind of interesting artwork. Lovely line drawing. So that's mu. That's the mean. That is what we're solving for. The level given 2 different uncertainties about GPA. And to put that in there, we need to insert a column. We did that before with the Poisson. And we learned that when you insert, it'll insert over here to the left of the cell. So let's insert a column there. There we go. Let's call it sigma. Okay. And we're not going to use max and min. This is really simple. We're going to assume, as we did in the lecture, a 0.5 level for each of these 5. And now we have pairs of different hypotheses. We have 5 pairs here. And now we're going to double it here. We're going to say what happens if uncertainty doubles. There's all sorts of reasons that uncertainty might double. We've been through that kind of recently, right? And the other thing is that, put this here, continue our formatting. It's better to do it now than then. Let's finish this up over here. Okay, and we can now say we probably have, so these are only 20% because we have only, you can look at it either way. 5 different hypotheses taken how many ways? Or you could look at this as intervals. Let's go 2 times the intervals, 2 times 4. There we go. 2 times the intervals plus 2. That should give us 10, right? Okay. And then just copy this down. Because we actually have 10 hypotheses. I might have used 5 in the lecture. It almost doesn't matter. But I'm doing this to make it a proper one because we're looking across all of the different pairs. Each one of these is a unique, mutually exclusive, and also completely exhaustive. Each one's mutually exclusive. It's a completely exhaustive list. So the hypotheses, just as before, are understood to be everything that we're going to be dealing with, and nothing more and nothing less. No over and under counting. Okay, now I kind of expanded these a little bit. So you can see that it's the probability of data being a particular level given an hypothesis. Now I think we had 3. I'm going to start out with 1 at a time and add them. Well, how do I do that without messing up, technical term, my products or anything else? Let's see if that happens. Well, we have one more thing over here to worry about. And that is probably this and this. There we go. Okay. So we probably are okay. What else do we have? Let's just run around the block here. These products go from F13 to K13. So F, that's the probability of this hypothesis, which is this whole hypothesis right there. And we can actually do differential probabilities of mu and sigma. Absolutely can do that, because we can further decompose the formation of hypotheses into 2 separate components, which taken together would feed the Gaussian curve that we have. Now these numbers seem to work okay. Let's see what we come up with. And I just want to check something out. These are all zeroed up. Ah, there we go. They finally do come in. These numbers are very, very small. Okay. Apparently. Let's look at all of these. Okay. Kind of can congregate down here. And notice that we have 5 here and then another 5. So they kind of come in this kind of pattern. And so just checking these out, we have 2 different sets. Notice the patterns here, a little bit hard to see. They tend to aggregate around 3.25 in this particular setup. And what we want to do is we want to take out some columns. I think we had 3. I want to take out 1, 2, 3 here. Let's see if we can do that. Okay, delete column. Okay, and this is still terribly messed up over here, as it should be, because this graph might not work. That's why I'm kind of showing it to you. It's kind of reversing itself, then going back up here. The reason for that is we have two different sets. And now we're going to have to do something much different than this approach right here. We have a two-dimensional set of parameters. We have mu and sigma, not just an x-axis of, in this case, average rate of laborers, lambda, or in the case of the binomial model, the proportion of water on that globe tossing experiment. Okay, so we'll have to play with that, and as we saw before, we're probably going to get rid of one more here. Let's do that. Okay, and so I think all of this, I'm showing this only because it's kind of nonsensical. You can see where the switch point is here. So we still have the same kind of problem. Reduce these here. There we go. Or easy to read. Now, we had, I think, a semester, which is the performance period that we typically have in higher education. We had 3 semesters, and I'm just going to make up 3 semesters worth of work now. One will be 3.5 grade point average, another will be 2, and the third will be 2.75. So it's going to be very, very close to the 2.75, right? So let's start with 2. It was a real rough semester. There we go. And now we need to put in an appropriate formula. Now, instead of the Poisson distribution, we're going to put in, and there's going to be 2 parameters here. We might as well just keep the G4. So let's type in, put in here norm, not for Norman, but norm. And the mean will be this number for the first one. And of course, we have to make the column absolute, or as if a constant. Don't want it to move when we copy this around. And also the sigma. So we have 2 components, and we also put a $sign in front of the column designator. We have to tell the robot behind this, SUF, it must be capped. Case. Okay. And it's 11%. Then we just copy this and paste all the way down. And we can see that for the 2, it very much congregates around 1.75, as you would pretty much, I think, expect. It's fairly close. It's closer to 1.75 than it is to 5.0, 0.7%. And so plausibility is almost a degree of closeness, proximity. We also have 2 sets here, going from 11 down to 0. It's practically 0 probability. And in the higher level, of uncertainty about performance, we have a higher plausibility of the 1, and even a higher plausibility of the highest performance, because there's more uncertainty. It could reach that. And that's a quality of the normal distribution. Now let's just check the numbers. We should have a normal distribution that looks like this. 1 equals 1 over 1 divided by, open parentheses, the sigma times the square root of 2 times pi, the Greek letter pi, 22/7 in the classical frameworks of ratio of perimeter to radius. Okay. Let's see if I've got enough. That should do it. There we go. 0.7978. And as I think I also said, whenever you see pi lurking in a formula, pretty good chance we're talking about circles, and we indeed are. This is the epicycle set of circles, and there's a whole set of series that are associated with the circle that we as data analysts should be aware of with these models, and that has to do with sines and cosines. Cosine is for on a unit circle. The cosine is, as we all remember, draw a line from the origin out to the edge of the circle. The x coordinate will be the cosine of the angle of that line with respect to the x-axis, and remember the ordinate, the y value, it'll be up the sine of that. Okay, sine and cosine work out that way, and sine squared plus cosine squared equals 1. The Pythagorean theorem all works out. So all of that is buried inside this formula, which is also kind of interesting in and of itself. And here we're going to multiply it times the exponent, or e to the minus 0.5 times the z value squared. Now the z value, double parentheses here, is theta 2 minus the hypothesized mean. This is centering, and then we scale this by the hypothesized sigma. Okay, that should work, except I need to square it, and that should work. Yep. Okay, that averages to 10%. Let's just check the numbers and see if they work out to be the same thing. Always do this. Don't assume anything. There we go. There we go. There we go. That's good enough. 798 is what we get. Okay, very cool. So we verified the normal distribution as it flows out here. Okay. We also have something interesting happening here, where we have a range. Here's the first 5 and a second 5. Now, as we did in the lecture, we need to put these side by side. So let's do that. Let's take all this apparatus and move it away. Make room. Okay, put it over here. There we go. Let's make room for mu's and sigmas. So we're going to put some mu's here. And these are going to be the same mu's that we have over here. We're going to see what we do. 4, 5. Okay, those are the 4 mu's. Here, we're going to put the 2 sigmas. There's 1 sigma. And here is the second sigma. I'm just taking it directly from the graph, the table rather. Okay, we're not going to put a graph together here. We might do that next week in another lecture. Okay, Now, what is this? These are these. Very, very, very pleasant. Okay, good. And these are the next series, starting with 1, going down through 4. And it's very useful to compare these side by side, a low volatility or low uncertainty environment about performance versus a high one, double by this metric, increases the plausibility of a very low score. But it also increases the plausibility of a very high score. Very interesting. That makes sense? Well, that's for us to discuss. I'm sure we can have a very fruitful discussion about that. And make a nice, very good. Now, we're not done yet because what we have here is a table very, very similar to the kinds of tables we have built before. We're going to make use of a property of hypotheses, that they are mutually exclusive, and not only that, completely exhaustive. We're only looking at 2 environments, high and low. There is no other set of environments about sigma. We're looking at a range from 1 to 4, equally spaced in 4 intervals, 5 nodes for performance. So those are the only ones that could possibly appear there, given our current state of arithmetic. Okay. But what is the probability of seeing mu? What is this probability? Probability of mu equals this. And that's all we need to see. Because it's going across both. Oops, I gotta put doesn't know what to do. So it's, well, it's kind of screaming at me actually. Okay. And there we go, finish the job. Can't see, finish it. This in front. There we go. Probability that mu equals 1. We also can search for the probability that mu equals 1.75 or 2.5 or any one of these numbers. So let me put this over here to the side. Okay. And since these probabilities are 4% in one environment and 9% in the other, it is not a both and, it is an either or. It's either going to happen in a low environment or a high environment. And this is the nature of looking ahead into the future. For example, we want to project what our performance might be in a low environment. Well, it would be 1 with that plausibility and 0.9 if the other environment occurs. So what is the probability of a mu equals 1? Well, we simply add them together. And it's 14%. And we see it goes as high as 43. That is the most plausible. Okay, that's the most plausible mu. And down again to 33, 9, and 2. Okay. Now, these happen to add up to 1. Let's see if they do. We have a probability distribution. I believe we do. Yes, we have a probability distribution. Can't help ourselves. As we add more data, this will change. Now we can make this into a heat map. we can make this into a surface. Not a very good looking surface. This heat map's probably going to be a little bit better. Now we have the probability of mu occurring. And this is a marginal probability. And we know what marginal probabilities are. They're in the margin of a table. Yes, we have a table here, and yes, it's a margin. Yeah, let's just do it like this for the moment. There we go. And now, if we can do that with mu, we can do it with sigma, right? Why not? Sure. Okay. So probability of sigma, we'll put over here. And we have several probabilities to consider for a sigma of 0.5. And we also have 5 probabilities to consider for a sigma of 1. These are all mutually exclusive and completely exhaustive. So we're going to add them together. There's no intersection there. There's no both and going on to make our life difficult. So put these here. And let's do this. These are just going to be the sum. So we're using the same probability rules that we've been doing for the last several sum of, okay, let's do this right from here down to here. That's 52%. Look at the split between the two environments. 48. They're almost evenly split. The 0.5 environment is slightly more plausible than the much higher environment. And when we combine that with the most plausible mu, this is the intersection. This is where they intersect. This is where they're intersecting. Make this light blue. And let's make this a light blue. The other direction. And the most plausible, and these, as you can see, are joint probabilities of mu and sigma. Okay, let's make this really stand out here. Oh yeah, let's make it yellow. There we go. Okay. So the most plausible hypothesis is 1.75 and 0.50. And we got that from looking at all of these hypotheses jointly. And that's the beauty of this system. They are jointly, they're literally that little piece of data, that one semester's worth of performance at a 2 is being shared across all of these potential hypotheses as they mix. Now that's the important point there. Same system that we've done before. Let's hopefully see if this works. Let's do an insert. No, I'm going to insert over here. That would be a safer bet. Okay. Insert another column. Let's put in another semester's worth. Well, let's say we go in the other direction, 3.5. Okay, that means we have to copy and paste those likelihoods. And we see things have changed a bit over on the right. In fact, I don't want to use any of that background coloring. Say no, Phil, that's all. Phil can't be here. And now look, we are now moving things away from the 1.75. We're moving them up. Okay, we're moving them up. And we have, again, the two different, here we're now up to 2.5. Why? Well, we went from 2 all the way up to 3.5, and that's pretty close to the 4. All right, fine. So there's more probability there going on, and not much going on over here. It's far away. It's closer to the 2.5. My question is, why isn't it closer to the 3.5? Why? Because we still have the 2 in there. That's why. Okay, fine. So far, so good. And we see the splits are a bit different as well. We're moving closer to the high volatility environment. Why? Because there's more, the data is wider. Quite literally, the range is wider. So the higher volatility environment seems to be a bit more, or quite a bit more favored. It's almost 70-30. It's more 70-30 here. Split. Notice everything still adds up to 1. The most probable is going to be here at 29. My probability at 29 is the most probable, and it also represents the most probable mu and the most probable sigma. Those are all going to be consistent in this hypothetical deductive process. Hypothetical objective. Sorry, Andy Gelman and Cosmo Shalizi, who did quite an interesting analysis of the type of thinking that goes on here. And we're going to add one more. I've forgotten what that was. Well, I think that was 2 point. I'm just going to put in 2.75. Okay. Oops, I don't want that. Get rid of that up here. There we go. Reverse that. Control C. And up and down. And let's see if things still make sense. Now it's 60-40. Well, that makes sense. We moved down from 3.5 down to 2.75, closer to the 2. So still the high volatility environment dominates. And what still dominates? Yeah, definitely the 2.5 grade average. So we would literally be forecasting that a 2.5 grade point average is reasonable in a high volatility environment. Okay, with these probabilities. That's what we would be saying. And if we wanted to ask the question, well, with this data, what would the next one look like? That's a good question. We'll save that for another lecture. But you can see how we can use this. We can continue to update as we go semester to semester to semester. And as we advise, well, employees, partners, business partners, certainly, students, workshop participants, people looking for accreditation, you say, hey, keep moving here. But notice the understanding of what is a high volatility versus a low volatility environment. Thinking about the portfolio of typical collegiate work, a high volatility environment might be one in which a student is well outside her or his comfort zone. Okay, you're all in business analytics or marketing or French, and now you're outside of that, and you're not very good at the fundamentals yet because you haven't had that. You've had no reinforcement of those fundamentals, and you certainly haven't mastered them. So that could be a high volatility environment. Also, you might be putting into the mix the need to work the graveyard shift from midnight to 8. And so you might not be quite up to par one semester trying to make ends meet. So all of these would contribute to the low versus high volatility environment. So this is an interesting kind of way to model that question that we posed. And I hope you enjoyed the deployment. Can't use that, it was told. The implementation of what we did in the lecture here. I just want to make sure that we have a record here of formula text for this particular instance. There we go. That's, oh gosh, 2 A's there. There we go. It was norm dist. And over here, we verified it. And let's just put that formula there too. And there it is. So we've documented ourselves to some extent. And with a little bit more formatting, we are pretty much done. The data now is all the way across. There we go. And I suspect we can say we're pretty much done with this. So we repurposed the an 11 grid model into a 10 grid with 2 different parameters now, and came up with another approach here. Now, by the way, we can use an index and a match to get these, and that might be an interesting thing to do because we are indexing this thing here. Actually, the way I typically do that with multi-parameters is I create a unique key to index on. The key here would be a combination of this cell and this cell, and combine this 0.5 and 5 into the same format of that key, and then search for it. Okay, that's another way to do it. Another time, should be interesting. Okay. And I'll leave you with that. And again, thank you very much for your very kind attention. And have fun implementing a much more sophisticated model, one that is in wide use across all areas of science and data analysis.